Hi, I'm Jackson Eisenberg, and I am the mentor for FTC teams 9686 and 10396. Today we'll be looking at applications of drivetrains, and the first drivetrain we'll be taking a look at is your standard Mecanum drive. So with the Mecanum drive, you have a lot of different ranges of motion. You have sideways movement, diagonal movement, forward movement, and of course, can't forget about turning. Now, let's assume that we've, in the program, set the directions of the motors, or wheels, whichever, so that these are moving this way by default and these ones are moving this way by default. Now, for Mecanum drive, the diagonals are our motor groups in this case. Each diagonal acts as a motor group. As you can see, they have the same orientation. The rollers are in the same direction. Now, the rollers apply what is known as a slippage force. I like to call it a slippage force because the rollers have this slippage. So as it rolls, so as the wheel moves forward, it applies this slip as it moves forward. And so that causes it to slide over to the side. However, that slippage force can be balanced out, or it can be negated by other slippage on the other wheels. So let me visualize that for you. Let's say that our slippage force can be represented through a vector. So first of all, let's take a look at what direction these wheels are moving. These wheels are moving like this, these are moving like this. Let's say we're moving forward. Okay, so here's the direction of the robot, forward. Okay, the robot's moving forward, and these wheels are moving forward, and these rollers are moving this way. Okay, the rollers are moving this way. And here the rollers are going to be moving this way. So let's write that out as a vector. There's the direction of motion, right? So now you have the directional vectors for the rollers. But we want to break down the directional vectors into two components. The first component being the forward velocity, or the velocity of the drive. We'll refer to that as the drive velocity. And the slippage force, and we'll refer to that as the roller velocity. So we have the forward velocity, otherwise known as the drive velocity. So we have the drive velocity for each wheel, and then we have the slippage velocity. So if we're breaking this down, this is moving this way, so this component is going to be this way, this one's going to be this way, these are going to be this way. Okay, as you can see, these two forces cancel out. These two vectors will also cancel out. And so what we're left with is just these drive vectors. Okay, just the drive velocity is all that's left, and so we're driving forward. Now, how do we determine what the directional drive is? Well, let's think about it in terms of the direction, right? So, if we think of the joystick, right? We have two joysticks. Our first joystick being the drive stick and the other one being the turn stick. Let's refer to the drive stick, okay? If we think about it as a unit circle, right, then let's just look at a few significant points. Now we have all of our angles from negative pi to pi, right there. So we have theta is what we'll refer to that angle as. The angle that is made with the on the unit circle, the angle that the joystick makes on the unit circle, and then we have then we want to know what do we want to find? Well, we want to use the trigonometric function. We want to use sinusoidals in order to determine the speed. So as a sinusoidal, we're going to use sine. So we're going to use the sine, okay, the sine of theta plus pi over 4. Okay? Then we're going to use the sine. Negative 3 pi over 4 is here. That's negative root 2 over 2. And this one will be root 2 over 2. Okay? This one, negative 3 pi over 4, add pi over 4. That gives us negative pi over 2, which is this one. That's just going to give us negative 1. This one's going to give us 0. This one's going to give us 1. This one's going to give us 0. You can just tell. Now, theta minus pi over 4, well, that's going to give us negative pi. That's 0. This is going to be negative pi minus 4 and minus pi over 4. That's negative pi over 2. That's negative 1. This is going to be 0. And this is going to be 1. Okay. Then the rest is self-explanatory. Negative root 2 over 2. This one's going to be negative pi over 2 minus pi over 4, negative 3 pi over 1. This is negative root 2 over 2. This is going to be root 2 over 2, negative root 2 over 2, root 2 over 2, root 2 over 2, negative root 2 over 2, and root 2 over 2. Okay, and as you can see, it repeats at pi because pi is equal to negative pi. This is what we get. As you can see here, this is what matters. Negative 1, 0, 1, 0. Okay? 0, negative 1, 0, and 1. Now, when we have the stick going at this angle right here, pi over 4, right there, what is it that we want the wheels to do? Well, we only want the wheels to move in this direction. What vectors are going in this direction? It's these vectors going in that direction. And we only want it to go at 45 degrees, so we only want these to be moving. So the speed of this is 0. This is going to cause our robot to move 45 degrees, otherwise known as pi over 4 radians, right? So that is how we determine that. So that means that we want this, we want this to be powered with 1, this to be powered with 0. Let's refer to this chart, pi over 4, this chart, to see what we get when we apply pi over 4. 1, 0. Oh, so we get 1 and 0. That's what we want. So we want this sine of theta plus pi over 4 to be applied to the downwards diagonal, and sine of theta minus pi over 4 to be applied to the upwards diagonal. We also need to take into account the radius of the joystick, right? Sometimes the joystick isn't at its maximum push throttle, right? It might be halfway there, or it might be a third of the way there. You don't know. So, in order to account for that, we need to also take into consideration the radius. So first of all, we already know that the downwards diagonal is going to be some function of theta, okay? And then the up is going to be another function of theta. And we already know that this is related to the sine of theta plus pi over 4, and this one is related to the sine of theta minus pi over 4. Now, if it's going at 50%, right, then we want the speed that it's moving at to be 50%, correct? Well, if we want this to be moving at 50% of the speed, then we just multiply it by that, then we just give it that multiplier, right, 50%. So we just need to find the radius. So how do we get the radius? Well, if we take a look at the vector, right, here, so this is the joystick position. We'll refer to that as the vector form x, y. Okay, so here's our vector, x, y. Now we need to determine the radius here. So how do we do that? Well, there are a bunch of different options. In programming, you can use the hypotenuse function, math.hypot. Okay? And in order to get the angle, you would use math.atan2 to get negative pi to pi. Okay? Which is what I recommend, using math.hypot and math.atan2. So, what you're going to do is you want to take the magnitude of the vector. The symbol for magnitude is this. You do double bar, x, y, like that. We'll refer to this vector as jvac, the symbol being this. This is jvac. So, we want to find j, which is equal to the magnitude of jvac, okay, which is equal to the magnitude of x, y. Well, we learn in class that for two-dimensional vectors, we can find the magnitude, or say, imagine that this is broken down into two different things, with this being the angle, right? Two different vectors, horizontal and vertical. This is a multiple of I hat, and this is a multiple of j hat, which are the two basis vectors for your two-dimensional space, being your coordinate plane. I hat being this, and j hat being this. And then I hat is just 1, 0, and then j hat is just 0, 1, like that. Okay? In your two-dimensional space. Right? So this is a multiple of I hat, and this is a multiple of j hat, because you can always write your vector. If it exists within two-dimensional space, right? Then it can be written as a linear combination of your two-dimensional basis vectors because it exists within the two-dimensional space. We have x and y. This is representative of x, and this is representative of y. We learned this from Pythagorean theorem. X squared plus y squared is equal to c squared, but in this case we'll refer to this as j. This is what we want. We want to know j. So if we're referring to these as just j, x, and y, then we want to find that. Based off of our vector decomposition, right, that our x vector and y vector are here. Okay? This is x back and y back. Right? So we know that x back is going to be some multiple of your I hat. Well, what is that going to be? It's just going to be x times I hat. And then your y vec is just going to be y times j hat. So in that case, we know that this is just going to be x, 0, and this is going to be 0, y. How do we determine the magnitude? Well, we can, 1, do Pythagorean's theorem. What is that? X squared plus y squared would be equal to j squared. So that means the j is just the square root of x squared plus y squared. But this isn't really that much, or that isn't closely oriented with our vector math, right? We want to figure out, we want to determine it in terms of vectors. So what we would use is we would find the square root of the dot product. That is how we would determine the magnitude. The dot product of the vector with itself. So the dot product of the vector with itself is you just take the vector v, take the transpose of that, and just multiply it by v. So we have v, we have just the transpose of v times v. The transpose of j vec times j vec, and that will give us the dot product, which is j squared. This would be equal to x, y times x, y, which is x squared plus y squared is equal to j squared. So it's just going to be the square root of that. Now we know that this function is actually going to be our magnitude j times the sine of theta plus pi over 4. And this is equal to j times the sine of theta minus pi over 4. Okay, but now that we've determined all of the directional motion, we need to account for turning. So we've figured out all the things about the drive stick. Now we need to account for the turn stick. For the turn stick, we only care about the x direction of the stick, because this is turning left and turning right. We'll refer to our turn stick vector as tvec. Our tvec is just x and then y, but all we care about is x, right? So, for example, we have the turn stick at 1, 0. So that is right there, right? So that means that we want it to turn right along with, say, maybe it's going forward. Okay, so it's going forward, and we want it to turn at the same time. So it's moving backwards. Now, when it's moving backwards, that means that its direction is like this. This means that this vector, the roller vector, the overall vector, or the average vector, is in the opposite direction. So our drive vector is down. So our drive velocity is downwards now. So all of these should have a drive velocity downwards. So now we're going to point in the opposite direction of the rollers. So these are going to go like this. So now we know that this is our new vector decomposition. Okay, we have our new vector decomposition right there. Now, we want to account for the turning 1, 0 with our drive velocity, let's say jvac being 0, -1. Okay, so now how do we account for that? Actually, not -1. Let's do -0.5. D of theta refers to the front left and back right motors, or wheels in this case. And U of theta refers to our back left and front right. We want our left and our right. We know that the left speed has to be, we want that to be, say, if we have this being 1, 0, right? Being So our turn velocity is 1. We want it to go like this, which means we want this to be 1 and this to be negative 1, which means that we're subtracting t here and adding tx here. So minus tx here, add tx here. So for all the left motors, we get that this is j sine of theta plus pi over 4. Okay? FL is equal to g sine theta plus pi over 4. Alright? And then this is going to be plus tx. Then we have our back left motor. This is going to be j sine theta minus pi over 4 plus tx. Then we do front right. That's j sine theta minus pi over 4 minus tx. And then we have back right is j sine theta plus pi over 4 minus tx. And so this right here is our robot-centric velocity for our front left for all 4 of our wheels. Field-centric means that we're referring to the orientation of the driver rather than the robot. So robot-centric would mean that this is 0 heading right here. So this is the direction the driver's facing. The robot is facing this way, and the driver pushes forward on the stick. In robot-centric, the robot will move like this. And in field-centric, the robot will move like this. Okay? No matter the orientation of the robot, in field-centric, if the driver pushes forward on the drive stick, the robot will move away from the driver. Well, the angle that it's making is pi over 2, right? And the angle here is negative pi over 2. So the angle it's moving here, respective to there, is pi over 2. But if this is actually pi over 2 with the joystick, if this were robot-centric, then this is what? This would be pi. Right? This would be pi. So essentially what we do is we take the angle of our stick, we'll refer to that, right? That's theta, and we subtract the current heading, phi. This is our new angle. We do theta minus phi. And that will give us our field-centric code. And I can prove that to you. Let's replace all of these with theta hat. We'll say that this is theta hat right here. Okay? Theta hat plus pi over 4. Now, let's say that our robot is currently has a heading of phi is equal to negative pi over 4. Okay. And let's say that the driver pushes the stick to go at 3 pi over 4. So that's theta. So our theta hat is going to be what? 3 pi over 4 minus pi over 4? Pi. So theta hat is going to be pi. Now, if theta hat is pi, then let's take a look at how the robot is going to move relative to itself. So now let's rotate the axes. Right? Let's rotate the axes right here. This is now 0. Okay? This is now pi over 4, and this right here for direction of motion, is now pi over 2. Right? But then we need to think about it in terms of relative to the joystick. So this is pi over 2. This is 3 pi over 4. And this is pi. Right? So now, let's apply the power. We have j, we'll say is 1, and t, we'll say is 0. Right? So now we have the sine of theta hat, which is pi plus pi over 4, negative root 2 over 2. That means it's moving like this. If our robot is moving like this, right? Moving like this. We want it to move like this, right? This is going to give us what? Negative root 2 over 2. This is going to give us what? What's it going to give us? Pi minus pi over 4 through pi over 4 root 2 over 2. So this is going to give us negative root 2 over 2. So we know that this is going to go in the negative direction. Negative root 2 over 2. This is going to go root 2 over 2. This one is going to be negative root 2 over 2. So we have front right and back left going at root 2 over 2. And the front left and back right moving at negative root 2 over 2. So that means it's going like this, and this is going like this. What does that do? Well, let's look at the vector. Right? Let's take a look at the vectors that it's making, and let's see the direction. We want it to move this way relative to the robot, right? Pi over 2, right? Moving pi over 2 relative to it, or pi in this case, right? Because we'll say that this is 0, that's pi, right? We want it to move pi in the direction of pi. Okay, this is the direction we want it to move. So let's see what direction it actually is moving. Well, these two are doing what? These two are moving down, which means that this is the direction, which means that this is the direction of that. Right? So we don't care about this right here. We only care about the decomposition. These are moving forward. Right? Which means that this is the direction of motion, which means that this is our vector here. Now, what do you see here? Well, these two cancel out, and these two cancel out because they're moving with the same speed, root 2 over 2, but they're in the opposite direction, so they cancel out. Then all we're left with is this direction right here. Look at that. And that's the direction of our motion. And so that is the application of drivetrains for a Mecanum drive. So this is the code that, or mathematics, that you want to use in order to create your Mecanum drive.